Okay, sorry online people, I forgot to start the video and you missed like 2 slides. It's not too bad. If you want anything on those 2 slides, email me and I'll explain it to you. Okay, so we're picking up here. Interstellar matter is the first thing we're going to talk about. Interstellar means between the stars. So we're talking about matter that's not really part of a star. It's not part of a solar system or a galaxy. It's just kind of out there in the void. There's several different ways that it can exist. Strings and clumps of matter, which are actually difficult to see because they don't have a lot of mass. They're not reflecting a lot of light. And then you get your nebulae, which are basically big clouds of matter. And we have several different types. They mention bright and dark here. These are mostly made of hydrogen and helium. If they were made of heavier elements, they would be near a bigger star. They would probably be pulled in by that star or by its planets surrounding it. And so most of these nebula are just hydrogen or helium, which, by the way, even today are still by far the most abundant elements in the solar system, or in the universe, not just the solar system. Most of the universe is made up of just hydrogen and helium. Now, they're going to go through a couple different ones. They have bright nebula, which release a UV light. They appear more red because of the UV light that they emit. So UV is on the red side of the spectrum. They're active star-forming regions. So these are like condensing down and starting to produce fusion on the inside. And maybe one day in the far future, we'll end up becoming a star. Then you get your reflection nebula, which are blue. The reason they appear blue is because they're reflecting light on the blue end of the UV spectrum, which is much easier to reflect. It's easy for us to see, and so we can see them pretty well. So these are your blue reflection nebula. Then they have their planetary nebula. This is actually part of the life cycle of a star. They're not planetary because they will become planets, or it's just because they look like planets. They're nice and spherical shaped, and they resemble giant planets. This one, I'm not 100% sure, but this one looks like the God's Eye Nebula. And so if you've ever seen a picture of that, it's pretty neat looking. I don't know that this is exactly that one, but the God's Eye Nebula is a pretty famous one. Now, they get to dark nebula. These are dark not because they have dark matter. They're not really associated with dark matter. They call them dark because they're too distant from the stars to be illuminated. They appear as opaque objects against bright backgrounds. So essentially, we don't see them, but we see stars disappear behind them. Or we look out into space and we see an area of space that has very little to no stars in it, where everything else around it has a bunch. So we know that there's something there blocking out those stars, and that is more than likely a dark nebula. So kind of we know of its existence by omission rather than by directly seeing it. So they ask, why are the reflection nebula generally blue? Because they're scattering that short wavelength blue light that's actually pretty easy to see and easy for them to scatter. Now, we get to the Hertzsprung-Russell diagram. This is a diagram you will see in the homework and you will see on the test. You will probably also see it on the final. This is a very important diagram. We talk about it a lot. As far as diagrams go, it's busy. It's got a lot of stuff going on. You'll notice all 4 axes have different numbers on them, and you have several different categories within the graph itself. So just to start, surface temperatures here on the bottom, and it's backwards from the way we normally put graphed bars on. So you have your lower temperatures on the right and your higher, hotter temperatures on the left. You have luminosity here. So these are your less bright stars and your more bright stars. You have spectral class, which is just how we group things. And just to make it not easy, they don't even group them in order of letters. It's M, K, C, F, A, B, O, which, to be fair, we won't use this very much, if at all. But know that they're up here, and these letters stand for something, which is why they're all out of order. If they didn't stand for something, hopefully they would be like A, B, C, D, E, F, G. But because they're not, I imagine they stand for very specific terms for these stars. And then you have your absolute magnitude. Absolute magnitude as opposed to relative magnitude is basically like relative magnitude would be how bright a star is while we view it from here on Earth, which could be deceiving because if it's very, very far away, it may not look very bright. But when we do the math on it, we might discover that it's actually a very big, very bright star. We just don't see all that because it's so far away. So to kind of equal that out, we use absolute magnitude. We determine how bright the star would be from a particular distance. I don't know if it's 1 AU or a certain number of light years. I don't remember off the top of my head. But it kind of equals the playing field. And so we can know relatively how bright it is from a particular distance, and we can compare them in a better way. My mask is not staying where I want it to stay. So let's look at the inside of the chart and kind of look at each of these different sections, because we're going to talk about these in just a second on the next slide. You have the main sequence right here in the middle. Our sun exists in the main sequence. In fact, our sun is just about as average as it gets. 90% of the stars that exist are in the main sequence. Ours is right in the center, not one of the bigger ones, not one of the smaller ones. It's just average. And so when we talk about us on Earth living in the Goldilocks zone, not too hot, not too cold, just right, we live in the Goldilocks zone of like a Goldilocks sun. Not too big, not too small, just the right amount of light, nice and yellow, not crazy blue or crazy red. It's nice. We're average. We're just very average. So these are your main sequence stars. You can see the smaller stars have the lower surface temperature. They're not quite as hot, and they're not very bright. And so the smaller you are burning fuel, but you're burning it very slowly. You're not producing a lot of light. The bigger stars are going to have higher surface temperatures. I hope you all know that the blue part of any flame is the hottest part. And so the blue stars are definitely going to burn the hottest. You also have some red supergiants that are very large and put off a lot of light. So this is your main sequence. Here's your giants and your supergiants, larger, but not quite as hot in temperature as the blue stars, but they do produce a lot of light. And then down here you have your sequence of white dwarfs, very small, very dense. Some of them have very hot temperatures. Some of them have cold temperatures. But in general, they're not super bright. They're just tiny little stars. So they go through the different parts of these. As I mentioned, most stars fit in that main sequence. There's not a lot of deviation from that. You do have some red giants and some white dwarfs, but almost everything falls in that main sequence of stars. And ours is right in the center of the main sequence, a very average star. You get your giants or red giants, which we'll kind of go over what those are and why they're the way that they are in just a second. They fit into the life cycle of a star. And then you have your white dwarfs, which are fainter than your main sequence stars. They're very small, which they don't mention here. They're very dense. They're about the size of the Earth. So remember back in the other chapter, I mentioned that if Jupiter were 10 times bigger, it would be a small star, right? It would have enough gravity that you would have fusion happening in the center. It would be releasing light. So you have some stars, white dwarfs, that are about the size of Earth, which is much, much smaller than Jupiter. So you know that if they're producing fusion, if they're producing light, they have to be very, very dense. All of this matter times 10 squeezed into the size of an Earth, which is really small. And so they're going to be extremely dense. They do mention that not all of them are white. Some could be blue, some could be more red. It's just the size and the general lighter color that creates the white dwarf name. Okay, so stellar evolution. How did all of this form? How did we get to the point that we're at now? Stars exist because of two opposing forces. Gravity, obviously we understand gravity. The more mass you have, the more it's going to pull in and try to center everything. The opposing force to gravity is the thermonuclear energy, or essentially the constant sun explosion that's happening. When you blow something up in the way that the sun is creating its nuclear fusion, it's an explosion. We produce just a fraction of this amount of energy in like an atomic bomb. And so that outward motion has to be counteracted by something, and that's gravity. So in a stable star, you have the same amount of outward push from that fusion as you do an inward pull from the gravity that's created by all the mass. And so they kind of talk about that when it talks about balancing. But to get a star, you start off in the birth phase. You have a nebula, that interstellar cloud. The inner part of it has a little bit more density than the outer part. You start to get contraction, from gravity. As your gravity adds to that contraction, you get more atoms running into each other. You get your temperature rise, and that temperature rise leads to the beginning of a star, as we call it a protostar. So the proto part refers to like the beginnings of, like if you were to make a prototype, that would be the thing that you make before you make the actual real one. A protostar is the beginnings of a star, like a baby star. Not baby in size, but baby in lifespan. So your protostar has more gravitational contraction. The more stuff you get in the middle, the more the gravity, the more it pulls in stuff from the outside, and it's just like this snowball effect of gravity. Eventually, your core reaches a certain temperature, 10 million degrees Kelvin, and your hydrogen nuclei start to fuse. So like I said, early in the galaxy, early in the solar system, you only had hydrogen and helium. That's what begins when you have your star. I guess I already had one over here. This process is called hydrogen fusion, and we would like to do fusion. We're working on getting fusion here on Earth. It'd be extremely cheap energy. It would produce almost no toxic byproducts. That being said, it's very dangerous because you have to recreate the conditions inside a star in a lab in a safe way, which isn't really happening right now. We're getting closer, they say, but like for the last 40 years, we've been 20 years away. And like every 5 or 10 years, they're like, we're still 20 years away. So it may never happen. We'll see. But because of this reaction, your energy is released. You have outward pressure pushing everything out. Is balanced by your gravity pulling everything back in. And if those are balanced well, you have a stable star. If your star is unstable, it's not going to last very long. It's not going to fit into these sequences. So, main stage sequence, you have 2 different ways this can go. You can have massive stars or small stars. And actually, there's a medium star in between. But they're talking about different rates here. So think of these as vehicles, like vehicles we have today. The massive stars are going to be your big dually trucks. The small stars are going to be your small, like hybrid vehicles. Your big dually trucks are going to use their fuel faster. It doesn't matter that they have bigger gas tanks. They're going to be at the gas station more often than the smaller cars because they burn through that fuel at a much, much faster rate, despite them having more of it. We did not get very far, so we're going to have to lecture tomorrow for sure. I'm going to go ahead and stop this.